The sun is turning red. A good job you've done. But now you got.
Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. Now moving on to molecular orbital diagrams for atoms with a nuclear charge less than 8. So before we looked at this diagram, right, where we had the 1s, 2s, and then the 2p orbital, where we have the sigma, pi pi, pi pi, sigma arrangement in terms of the energy. But now, since the nuclear charge is less, the energy difference between the filled s orbitals and p orbitals is less. So the electron density from filled sigma orbitals and the antibonding sigma orbitals is concentrated along the bond axis. And so since the sigma pz orbital is also directed along the bond axis, there is electron-electron repulsion resulting in a higher energy sigma pz orbital. So you can see that right here, there's a higher energy sigma pz orbital, which used to be right here. So it got moved up and switched with the pi orbitals right here. And that's the only difference. Everything else looks exactly like when the z number is greater than or equal to 8. So the sigma pz orbital is therefore above the pi px and the pi py orbitals. And so remember that electron density in a pi orbital is concentrated away from the bond axis. The reason for that being that when you look at a p orbital, if the bond axis is right here, this is the area with the lowest concentration of electrons. So let's do an example here again. We did O2 for this example, so for here let's do B2. So diatomic boron. So we have the atomic boron on the left, atomic boron on the right, since it's homonuclear diatomic molecules, and the electron configuration for boron in the atomic configuration, remember we talked about this in the previous part when we were doing this, can be written as 1s2, 2s2, 2p1, because the total number of electrons the boron has is 2, 4, 5. Now to do the valence electron configuration, let's actually start filling this in. So boron has 5 electrons, so 1, 2, 3, 4, 5. Same on the other side, 1, 2, 3, 4, 5. And now we have 10 electrons to distribute in the center for B2. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now when we write out the valence electron configuration, or all the electrons that are involved in bonding, we're going to write it out as sigma 2s2, which is this one right here, and then sigma 2s antibonding, which is right here. And then finally we have pi 2p2, which is these 2 electrons right here. So once you draw this out, and 1s we don't actually write out because it's in the innermost shell, so it's not the valence electron configuration, and it's really easy to just follow the number of electrons that you put into the diagram. So now that we have this picture too, we can figure out the bond order again very easily. So bond order is 1/2 of bonding minus antibonding, so we have 2 and 4, 5, 6, minus antibonding, which is 2, 4, and we end up with 6 minus 4 equals 2 divided by 2 is going to give us 1. And so this means that B2 is found with 1 bond in between the 2 boron atoms. Again, we can see what kind of magnetic property this diatomic molecule has based upon how the electrons were distributed. And so we have 2 lone electrons right here that are unpaired since we distributed them based on Hund's rule. So this is going to be a paramagnetic molecule. This means that it is attracted to a magnetic field and it's considered magnetic. So now let's talk about HOMO and LUMO transitions, where Homo stands for highest occupied molecular orbital. So highest occupied molecular orbital. And Lumo stands for lowest unoccupied molecular orbital. So basically we learned that the interaction of any two atomic or molecular orbitals produces two new orbitals. And one of these new orbitals is higher in energy than the original ones, which is the antibonding orbital. And one is lower, which is the bonding orbital. When one of the initial orbitals is filled with a pair of electrons and another is empty, we can place the two electrons into the lower energy of the two new orbitals. And so the filled-empty interaction is therefore stabilizing for that particular molecule. So the two that interact when we're dealing with these different interacting molecular orbitals is the HOMO, the highest occupied molecular orbital of one molecule, and the lowest unoccupied molecular orbital of another molecule. So these orbitals are the pair that lie closest in energy of any pair of orbitals in the two molecules. So basically, if this was molecule A and this was molecule B, basically the highest occupied molecular orbital is the one that's completely filled, which is in the highest energy for that particular molecule. Whereas the lowest unoccupied molecular orbital is the first energy level up for the other molecule, where in an excited state, an electron could be put into that particular orbital. So generally, the energy difference between the highest occupied molecular orbital and the lowest unoccupied molecular orbital, also known as the Homo-Lumo gap. So basically this difference right here is generally the lowest energy electronic excitation that is possible in a molecule. So let me just write that right here. Lowest energy excitation. So basically, the energy of the Homo-Lumo gap can tell us about what wavelengths the compound can absorb, because the amount of electronic excitation is dependent on this gap. Alternatively, measuring the wavelengths a compound absorbs in the lab can be used as a measure of this Homo-Lumo gap. So for most molecules that are not extremely symmetric, there are no degenerate molecular orbitals, which means molecular orbitals of the same energy. So molecular orbitals are a series of single orbitals of increasing energy. Since most stable molecules have an even number of electrons in a closed shell, nearly all molecules will have all their electrons paired in molecular orbitals. So this was a basic introduction of HOMO and LUMO transitions for you guys, which we might touch upon a little more in later topics.